Okay, now let's look at example. So let's say we have seismic hazard curve given by the figure on the right, on the left, and we have turned it around. So the horizontal axis is the probability of exceedance. The vertical axis is the spectral acceleration. The blue curve is for t equal to 1 second. Red curve, 0.2 second. Okay, so we select a level of annual probability of exceedance, 4 times 10 to the minus 4. Then we have these 2 points. Okay, so on the right hand side, we have the uniform hazard spectrum. Corresponding to frequency period 0.2, we have this point. Okay, so this point. Corresponding to period equal to 1, we have this blue point. So this. Okay, so now by connecting these points, we obtain uniform hazard spectrum. And this figure shows the comparison between Newmark response spectrum and the uniform hazard spectrum for a same location. Okay, so not for same location. The Newmark ground response spectrum is the standard Canadian Standard Association CSA spectrum, and these 3 curves are the uniform hazard spectrum for Pickering. It's close to Toronto, Ontario in Canada. Okay, so now you can see they are quite different. Usually, UHS, especially for UHS in Northeastern America, it's very rich in the high frequency. And 20, 30, 40. So between 20 and 40, we have this plateau here. Okay. For the Newmark response spectrum, we have the plateau at between about 1 hertz and 15 hertz. Okay, so uniform hazard spectrum, seismic hazard analysis, PSHA, and based on the spectrum and the modal superposition method. We will look at this in a moment. So peak responses of the vibration modes of the structure are assumed to be in structural dynamics. However, as we discussed earlier, since the spectral acceleration at different vibration periods on UHS are generally induced by different earthquakes, hazard analysis combining all possible earthquake locations, distance, magnitudes, and rate of occurrences. Okay, so we combined everything, so we don't know which earthquake induced this and which earthquake induced this. They are combined, and formation periods on the UHS are generally induced by different earthquakes. Therefore, it is inappropriate to use the first mode response from one earthquake on UHS, and then the second mode from a different earthquake on UHS. But although this is not rigorously correct, people have been using this for analysis. And if we use UHS for analysis, the results are overly conservative, very conservative. Earthquake on UHS, and then the second mode from a different earthquake on UHS. But although this is not rigorously correct, people have been using this for analysis. And if we use UHS for analysis, the results are overly conservative, very conservative. Okay, now we study seismic response analysis. We consider a three-dimensional model of a structure, and it's shown on the next page. So this is a three-dimensional structure, and each node has 6 degrees of freedom. 3 translational degrees of freedom, UN1, UN2, and UN3 is the node number. And the UN4, UN5, UN6 are rotations. Okay, so we have 3 translational degrees of freedom and 3 rotational degrees of freedom. And the structure is subjected to tridirectional ground excitations, UG double dot 1, 2, and 3. U1 and U2 are in the 2 horizontal directions. They are orthogonal, so we have right angle between these 2. Okay, and UG double dot 3 is in the vertical direction. Now, using what we studied earlier, we can, if we have n nodes, each node has 6 degrees of freedom, 3 translational degrees of freedom, and 3 rotational degrees of freedom. So in total, we have 6n degrees of freedom. Okay, so we can write our equation of motion in the vector form like this. And x is the relative displacement vector. Okay, so this stands for node. Okay, so xn is for node n, and in 6 directions, 1, 2, up to 6. Okay, so the first n is the node, and the second subscript is for degree of freedom. Okay, so now we have 3. We have ground motions in 3 orthogonal directions. So we use a summation here for each term. Okay, UG double dot 1, 2, 3. And I is the influence. Vector, and it transfers the effect of ground motion to equivalent force. Okay, so that's the contribution or influence of each ground motion on the excitation. Okay, so it's explained here. I, this big I stands for influence. Small I means the direction of excitation is the influence vector of seismic excitation in direction I. Okay, so in this case, II is a vector with each element being 1 to the I, and 1 to the I is delta I1. Okay, and this delta is the so-called Kroneck delta function. So delta ij is equal to 1 if I is equal to j, or 0 when I is not j. Okay, so that's a very neat notation. Okay, so now we expand x into x1, x2, x3. xi is the relative displacement vector due to earthquake excitation in the i's direction. Okay, since we have 3 directions, so we separate into 3 terms. And then we have the equation in the i's direction. Okay, so we have 3 of these equations. Okay, so this is a multiple degrees of freedom system, and we can use what we studied in the first half of the course to solve it. First, we look at undamped free vibration. So there's no mode on the right-hand side. Damping C is equal to 0. Okay, then we perform the modal analysis to determine the natural frequencies and the mode shapes. From the mode shapes, we form the modal matrix phi, with each column being the mode shape. Okay, then we have this. And we know that the modal matrix can diagonalize the mass matrix and the stiffness matrix. Okay, so we diagonalize the matrices. And if we assume that the structure has classical damping, then matrix C can also be diagonalized by the modal matrix. Okay, so we obtain modal damping. And now we apply a transformation. This is the relative displacement. Through the modal matrix, this would be the modal displacement. Okay, so now Q, and normally we like to multiply by a term. This term will be clear in a moment. Okay, so Q is little qi is actually the modal displacement, but we scale it with a gamma. Okay, so when we substitute in, gamma is equal to L over M, and L is given by this. Okay, so that's a phi k transpose times M times II. this or this
Gamma is equal
is the earthquake
to L.
excitation factor.
L is given by
And it quantifies the contribution of earthquake excitation in the ice direction to the modal response QNJ, the nth node in the J direction.
is the earthquake.
Okay, so now here we have two notations. One is NJ, one is K.
And
NJ is the two subscript notation. N stands for node, the nth node. J is the direction, so NJ is node direction. And or we can use the one subscript notation, K.
So now here we have two notations. One is NJ.
Given this. Okay, so this is useful
Subscript notation. N stands for
when we want to know the position of the quantity in the vector. And we have one subscript. The two subscript notation is useful in describing the meaning of the quantity in terms of node and direction. And the one subscript is useful when we want to know the position of the quantity in the vector. Okay, so
Notation is useful.
L divided by M gives us gamma, and this gamma is the modal participation factor, and this characterizes the contribution of the node. Okay, now if this value is small, then the contribution from node K
L divided by M
is small. If this value is large, then the contribution of node K is large. Okay, so that's the modal participation function. How much?
Okay, now if this value is small, then the contribution from node K
How much is the node?
is small. If this value is large,
Participating
contribution of node K is large. Okay, so that's
in the response.
participation function.
Okay, so this value is very useful. Okay, so now when we apply the transformation from relative displacement to the modal displacement, we end up with this. So finally, we have a system of equations. Okay, since we have K equal to 6n degrees of freedoms, we have 6n equations. Okay, and for each direction. Okay, so I is from 1 to 3.
System of equations.
So I here and K
Equal to 6n degrees of
for the mode. Okay, so I is the direction of
and for each direction. Okay, so I
excitation.
is from 1 to 3. So I here and K for the mode. Okay, so I is
Okay, K is the
direction of
mode. Okay, so now we can solve this using Duhamel's integral. Okay, so this is Duhamel's integral, and we need this integral. If you recall what we studied last week on the ground response spectrum, this is the maximum value. Is the no.
This integral, if you recall what we studied last week on the ground response.
So that's SV in direction I and corresponding to omega k. Okay, so the maximum value of this integral is the velocity ground response spectrum in direction I. Okay, so now once we have this, QKI is given by this. Okay, now we introduce two methods for solving these equations. One is the time history method, and the other is the response spectrum method.
In direction I. Okay, so now once we have this, QKI is given by this. Okay, now we introduce two methods for solving these equations. One is the time history method.
Okay, so in general, we have two methods, the response spectrum method and time history method. Okay, we will quickly go through the time history method first. So that's our system. By transformation, we obtain a system of single degree of freedom system, okay, with a ground acceleration as our input. Now, if we solve this equation using the numerical integration for a given ground motion, okay, we can numerically integrate this equation to obtain y and t. Now, if we find this, we can use modal superposition to combine the results to find the response of node M. Okay, so we combine all of them, and then you can pick up the maximum response in node M. Okay, in node M, and then the maximum response is the maximum response for all the nodes. Okay, so to do this, we would need the ground acceleration. There's a second method. This method is using modal decomposition, okay, modal superposition, to decompose the equation of motion into a system of single degree of freedom system. So here we only need modal damping. Now there's a second method. It's called direct time integration method. So we start with the matrix equation, and then we perform numerical integration for this system. To do this, we have to know the damping matrix. The damping matrix can be represented by the so-called Rayleigh damping. And it is the combination, linear combination of the mass matrix and the stiffness matrix, alpha and beta. with alpha and beta as the coefficients. And in many commercial finite element software, K can be a nonlinear matrix. So the stiffness matrix K can contain nonlinear elements. For example, in software Stardyne, you use the Diary 6 module. It has a nonlinear spring element. Okay, so now if we integrate this, we can solve for the displacement. This method is useful for nonlinear system because modal analysis is only for linear system. If you have a nonlinear system, you have to use the direct time integration. Okay, so there are many different methods. We cannot go into detail, but usually we use a commercial software such as Stardyne or Answers to perform the integration. In both cases, we need to have the ground motion acceleration. Okay, so now we spend some time to discuss earthquake ground motions. Seismic response history method has been widely used for seismic design and qualification. And to realistically characterize the seismic hazard environment, representative ground motion time histories are required. And we have three types of ground motions. One is the actual earthquake records. And obviously this is the most desirable because it is real earthquake. However, a number of actual records are required to meet the acceptance criteria. We will talk about acceptance criteria in a moment. And in many regions, for example, in northeastern America or in Jiangsu province, there are very few actual earthquake records available. So this method may not be feasible. The second method is synthetic earthquake time histories using stochastic methods. So this is a pure stochastic method to generate ground motions. And in this case, only a small number of parameters are used to characterize the ground motion, which can never be complete. In some codes and standards, pure synthetic earthquake time histories are not allowed. Okay, so this is not very desirable. Somewhere in between, we have modified earthquake time history based on actual earthquake. So we use some real earthquakes.
谢老师，
Yes.
这个我这个屏幕上好像那个显示的还是您之前就是讲那个VR 那个PPT，
是吗？结束共享，
就是还是在讲那个积分。
现在行了吧？
现在可以了。
它应该自动跳的，行 ，OK， 谢谢。Okay, so the third is the modified earthquake time history based on actual earthquake records. And this is usually the preferred method because it is based on actual earthquake records. So it preserves the characteristics of actual earthquake records and by modifying the real earthquakes, they also meet the acceptance criteria. Okay, and you can perform the modification in the time domain or in the frequency domain. In the time domain, there's a Fourier-based approach. So we expand the ground motion into a series of sine functions. And then we modify the amplitudes and the frequencies of these sine functions so that they match with the target spectrum. And then we multiply by envelope to make it non-stationary. And this is mainly used in the 60s and the 70s. And the second method is the wavelet-based method. It's similar to the Fourier method, except that we decompose the ground motion into wavelets, 小波, and then we add or subtract wavelets to modify the frequency and amplitudes. Okay, there's another method. It's the so-called Hilbert-Hwan transform. The Hilbert-Hwan transform was developed by Huang et al. In 1998. It can represent non-stationary data, such as earthquake records. It decomposes the signal into several components, and it transfers the signal from time domain to frequency domain. And Hilbert-Hwan transform is complete. That means it guarantees the degree of precision of the expansion. You can achieve the required accuracy. It's local means the amplitude and the frequency of each component are functions of time. And it's adaptive. That means we derive the basis from the signal itself. Hilbert-Hwan transform HHT includes two steps. One is empirical mode decomposition. The other is Hilbert spectral analysis. And HHT has been applied widely for signal processing. And we applied HHT to generate spectral compatible time histories. Okay, so the procedure is as follows. First, we need to obtain intrinsic mode function. This is through the so-called empirical mode decomposition. And so here we have a real earthquake time history. By applying a shifting process, we can decompose this into a set of intrinsic mode functions called IMF. Okay, so here it's a real earthquake record. And by applying the shifting process, we obtain 11 IMF intrinsic mode functions. Okay, so these blue curves are the intrinsic mode functions. So when we add these 11 mode functions together, plus a small residue in the pink color, we can recover the original earthquake. Okay, this is the definition of a Hilbert transform, and in the analytical form, it's a complex function. In the rectangular form or in the polar form, A is the amplitude, theta is the phase angle, and the derivative of theta is the instantaneous frequency. Okay, so we can recover our system or our ground motion through the intrinsic mode functions IMF. Okay, so with amplitude A and omega. And this shows the advantage of Hilbert transform. Okay, so let's say you have a signal like this. It's non-zero between 4 and 5 seconds. And HHT gives you the frequency component only between 4 and 5 seconds. But the wavelet, 小波, would give you, it has a lot of leakage outside 4 and 5 seconds. Okay, so we have a lot of leakage here. So it's not local. And for seismic analysis and standards and codes have some requirements. For example, ASCE requires us to generate a time history for 5% damping, and we have to compute over 301 frequency points. So if we have a frequency between 0.1 Hertz to 100 Hertz, we have 3 decades, 0.1 to 1, 1 to 10, and 10 to 100 over the log scale. Okay, so we need to have 100 points between each decade. So here we have 3 decades. We have 301 points between 0.1 and 100 Hertz. The PGA of the time history should equal or exceed the PGA of the design response spectrum. And the response spectrum of the generated time history should not fall 10% below the target or 30% above the target. Okay, so this is to make sure that the design is conservative, safe. And this is to make sure that the design is not too conservative. If it's too conservative, it increases the cost of design and construction. Okay, and there are some other requirements. Okay, so I'll show you the results first. Here we have the blue curve is the design spectrum from Canadian standard CSA N2 89.3 response spectrum. So this is the target. Okay, so we want to generate time histories, and the blue curve is the spectrum of the generated time history in horizontal 1 direction, and the blue is in horizontal 2 direction. So you can see they are slightly above the target black response spectrum. It does not fall 10% below, and it's not 30% above. Okay, so what we do is in the first direction, we select a horizontal time history by applying empirical mode decomposition, we obtain J intrinsic mode functions. And we find the amplitudes and the frequencies. Okay, so time history 2 is given by these. So we need to scale the amplitude and the phase angle, the frequency, to obtain compatibility with the target. We establish an optimization model, and the blue is the response spectrum of the generated time history, and the TP is at the selected period, and this TST means the target response spectrum. Okay, then we minimize the error. We minimize the error here. Okay, we biscale the amplitude and the frequency. We minimize the error between the generated time history and the target time history to obtain spectral compatibility. For second horizontal direction, we use the first time history, obtain IMF, find the amplitude and the frequencies. Now here we only perform a shift in the phase angle because the first time history is already spectral compatible. Okay, and then we minimize the error again, and the correlation coefficient between these two time histories should be less than a code specified value, for example 0.16. And for the vertical direction, we find an actual record in the vertical direction, decompose it to find the K, IMF, find the amplitude and the frequency. Now we modify the amplitude and modify the frequency to obtain spectral compatibility by minimizing the error, and with the constraint that the coefficient of correlation between V and H1 between vertical and horizontal 2 must be less than a code specified value. Okay, so that's the example. We select 6 real earthquakes, 2 large far-field earthquakes, 4 small near-field earthquakes. Okay, so these are the real earthquakes, and the 2 pink are the large far-field, and the top 4 are small near-field. Okay, so we go through the analysis and we obtain the spectral compatible time histories. Now you can see the generated time history has characteristics of the real earthquakes. So for example, this portion looks like this portion, right? This portion looks like this portion. Okay, now you check the error, and between the spectrum and the target. So this is 1, and they're slightly above. It's not 10% below and not 30% above. Similarly for the vertical direction. Okay, so we select 4 near field, 2 large field, and the response spectrum of the target is well matched. Okay, so I will stop here. I ask you a question. You can think about it during the break. Why do we use large field? And why do we use near field? What's the difference between large far field earthquakes and small near field earthquakes? Okay, so you think about this. We take a break, and please come back at 9 o'clock.
啊？
各位主权，
对，我就看一下。这是这样的写。
我说的是460啊。
嗯。
等一下，我就多个10，以前是不是多10块还是多
500？
后院就是多2个差多少？原来
人差10。我就记这个。然后是这个什么？
那个，哦，对，我知道，那个是什么？我作为那个2想8X 这个，然后看。那还有伦敦那个？
对，就是这个。没有到上网可看。
这谁？谁这一个哪啊？
是。
Okay, let's continue. For when earthquake occurs, we have seismic waves we discussed 2 weeks ago. Okay, and then when seismic wave propagates through the ground, The ground has a damping mechanism or filtering. So far-field earthquake, when it propagates to the side, so that means the distance between the source of earthquake and the side is large, far-field. Okay, so then this would give us, the ground would have more damping and more filtering. Okay, so this would give us more low frequency components. And for near field, because it's close, so the filtering is not significant. So we will have more high frequency. Okay, now the ground also has a damping mechanism. So you need a large far field to have effect on the site. Okay, if we have a small far field earthquake, when it propagates to the site, it becomes very, very small, not significant. Okay, and for near field, usually we don't have large earthquakes because we don't want to build our structures very close to the source of earthquake, to the faults. Okay, so now you can also see from here, for the blue large far field earthquakes, we have more low frequency components. And for small near field, frequency is higher, going this way, okay, and higher amplitude for high frequency. Okay, so if we can use both large far field and small near field, we have the advantage of both low frequency and high frequency components. Okay, so you can see here, when we combine them, we have characteristics from both the large far field and small near field earthquakes. Okay, so let's give you a brief introduction. So in your work or research, if you do need earthquake time histories, and you can review or restudy this part of the materials.
谢教授，你是不是有一篇论文
啊？这个
我说您是不是有一篇论文是讲了你这部分的研究工作？
哦，对，我们有好多论文做这个的，就过去好多年我都在做这个。
我给学生发一。
有挺多论文讲这个的，嗯。
我是说您自己的论文。
别的方法，最近2、3年。
好的，我看到过您的论文。
嗯。Okay, so now let's study the response spectral method. Okay, so we will not go through time history, and we use response spectrum as our input to obtain the response. Okay, so the seismic response spectrum method or analysis is concerned with the procedure for computing the peak response of a structure during an earthquake directly from the earthquake response spectrum. Okay, so this is also called a direct method. Or response spectrum method. Direct means we go directly from response spectrum to the peak response without using time history analysis. Okay, this procedure does not give exact peak response, but it provides an estimate that is sufficiently accurate for structural analysis and design. Now, based on our previous equation, this equation, the modal response is given by this integral, Duhamel's integral, okay? And then we want to evaluate, we can evaluate this numerically using the time history method. Now we use the response spectrum method. Okay, the maximum value is the maximum value of V, which is the velocity response spectrum. Or divide by omega, then it gives you the acceleration response spectrum. Or with multiply by omega k, you can get the displacement using the displacement spectrum. Okay, so now SV is defined as the maximum value of V or the maximum value of this integral. And we have introduced this as the velocity response spectrum last week. Here we have the relationship between A and V. There's a typo in this equation. Please correct it. Okay, so this is actually a V, and this is A. This is V, and that's D. Okay, so please change this. It's quite easy to remember. So let's say if D is sine omega t, V is equal to the derivative of D, so that's omega cosine omega t. Okay, and A is V dot or D double dot. So that's minus omega squared sine omega t. Okay, so we have a relationship in terms of omega. Okay, suppose these are three terms. Sine and cosine would be similar in this. Okay, so now once we have the maximum modal response, okay, this is the maximum modal response, and we can evaluate the maximum elastic force. The elastic force is related to displacement. Okay, so similar to a spring, F equal to Kx. Okay, so the spring force or elastic force is stiffness matrix times the displacement vector. And the displacement vector is V times Q in terms of the modal response. Okay, you can also change. There's a relationship between K and M. So the elastic force can also be written as this. Okay, so here it's in terms of the stiffness matrix, here in terms of the mass matrix. Okay, either one is fine. Now in general, we find the maximum value maximum modal response. Okay, so we want to find the maximum of something. It can be the elastic force or base shear, or the overturning moment. These are used in the design of the structures. Okay, so we want these. So usually we have a linear combination of the modal responses. Okay, so now if we have the maximum for Q, we want to find the maximum for Z. QK, the maximum values of QKs do not occur at the same time, so we cannot add them. Okay, we have to use CQC. We studied this when we studied random vibration. Okay, we used the CQC combination rule. So you have the maximum modal response, and for the case mode and the Kappas mode. Okay, rho is the coefficient of correlation between the case mode and the Kappas mode. Okay, so we have the coefficients alpha given here and rho given here. Okay, so you can use CQC to combine. Now, as an approximation, we can use SRSS. When can we have when can we use SRSS? When the modes are well separated. Okay, so the frequencies are not close. When they are not close, the coefficient of correlation would be very small, okay? So you can drop the cross terms. Then we only have these square terms left, okay? So that's SRSS. And the procedure is very easy. We look at an example to illustrate. Okay, so here we have a frame ABC with a rigid right angle at B and clamp to ground at support A. Okay, so we have a frame ABC and this is a rigid right angle. So that means it's always maintained at right angle. And we have a mass at the top at the point C, and it's clamped at A. Okay, it supports a lambda mass M at end A. No, it's at end C, sorry. Please change this at end C with 3 degrees of freedom, U1, U2, and U3. Okay, U1 is horizontal. U2 is also horizontal but perpendicular to U1, and U3 is vertical. Okay, so U1 and U3 are in the plane of the paper, and U2 is going out of into the paper, perpendicular to the paper. Okay, so now the weight of the frame is negligible. The flexural rigidity of both members AB and BC is EI. Both members AB and BC are rigid in the actual direction and portion. Okay, rigid. Now the frame is subjected to tridirectional ground excitations, UG1 double dot, UG2 double dot, UG3 double dot. And the ground response spectra follow US NRC RG 1.60. This is the US Nuclear Regulatory Commission regulatory guide 1.60. Okay, so and in both horizontal directions, PGA is 0.3. In the vertical direction, PGA is 0.2 because it is 2/3 of the horizontal PGA. Okay, so that's 2/3 times 0.3 equal to 0.2 G. And we use 5% damping. Okay, so we know the length and mass density, and flexural rigidity. We want to use the response spectrum method, determine the maximum absolute values of the relative displacement displacements x1, x2, and x3. And the maximum overturning moments m1 and m2. Okay, so the question is quite clear. We know all the properties of the frame: length, mass, and flexural rigidity. Okay, we have these directions. Now first we need to establish the equation of motion, and so we need to find the mass matrix, stiffness matrix. Depending on the question, sometimes it's easier to find mass matrix, sometimes it's easier to find the flexibility matrix. Okay, and K and F are inverse matrices. Okay, so in this case, it seems it's easier to find the flexibility matrix. Okay, so flexibility Fij. Give you 30 seconds to record the definition of Fij. What's the definition of Fij? So you apply a unit load in J, and we find the displacement in I. Okay, so for F something 1, we apply a unit force, F equal to 1 in direction 1, U1. Okay, so apply a unit force in direction 1. And then we want to find the displacements in directions 1, 2, 3. Okay, so the dashed line is the original structure, and so this is F11. So the displacement in direction 1 due to a unit force in direction 1. And everything is in the plane, so in direction 2 it's 0. Okay, now direction 3 is in the vertical direction, so we have this is F31, and because this is a negative, okay, so now we use the beam formulas. If you have a cantilever beam and you apply point load P, it gives you the deflection delta B and theta B, the rotation. If you have an end moment, the deflection and rotation. Okay, so now this is the same as we have the force applied here. Okay, so we look at this element, apply a horizontal force, And that's exactly this case. Okay, so we find the deflection PL cubic over 3EI, and the theta is PL squared over 2EI. Okay, so we find this. Now, BC remains rigid. Okay, so because it's rigid in the actual direction, so it's rigid. So we just need to add this part. Okay, so we can find the displacement, this value, and the deflection is this. Okay, now similarly, if we want F2, so we apply a force in direction 2, in the direction that is perpendicular to the paper or the screen. Okay, so in this case, we only have deformation in direction 2 and nothing in directions 1 and 3. Okay, so we apply a force. This is the same as we apply a force here and pull this. Okay, so you have this part, apply a force to find this deformation. Now look at this part. It's equivalent to you have a clamped beam under force F. Okay, so we can find this displacement. So these two add up gives us the total displacement F22. Similarly, we add apply a unit force in direction 3 and find the deflection. Okay, so now due to this force, it gives us a moment for AB. Okay, so now AB is under moment. The moment arm is L. So that's 1 times L. Oh, okay, I have it here. M is 1 times L. Okay, so we have this case. We have a moment at the end. We find the deflection and the rotation. Okay, so you can find the deflection and the rotation. Now this piece, BC, it has a rigid body rotation to here, and then under the load, it bends. Okay, so it has two parts. It has a rigid body rotation due to the rotation of AB. Okay, so we have this, and then plus the deformation due to bending. The bending is this case with point load at the end. Okay, so this gives us F direction 1, force in 3. Okay, and then this add up gives us F 3. Okay, and then we have the, okay, so the flexibility is determined here. There's a mistake here. This 3 should be 2, and that's 2. Okay, 3, 1 equal to this 2. Okay, so please change that. Okay, so we find the flexibility, each element, and you can write the flexibility matrix. Take inverse, we find the stiffness matrix. Okay, for the mass matrix, because we have a lumped mass at C, so the mass in direction 1, direction 2, and direction 3 are all M. Okay, so because we have only one lambda mass at should be C at end C. So the mass matrix is a diagonal matrix. MMM. Okay, so we have our mass matrix. Now once we have everything, we can write the equation. We know that F is equal to Kx or K. Maybe use a different for F. Okay, force is Kx, and then K inverse F equal to X. Okay, so this is the flexibility matrix. So flexibility times force is equal to displacement. Okay, so using this equation, displacement is equal to flexibility this is the force. That's the equivalent earthquake load. Okay, and we have earthquake loads in 3 directions. So that's direction 1, direction 2, and direction 3. Okay, so xi is fi1, so force in direction 1. fi2, force in direction 2, and fi3, force in direction 3. Okay, gives us the total displacement in direction I. And then you can rewrite this in the matrix form to get this, or separate this, okay, into UG1 and UG2, UG3 double dot. Okay, so that's our equation. You can see this is minus m sigma I from 1 to 3 I UG double dot I. Okay, so that's our general form. And here we derived this equation. Okay, now I are unit vectors. Okay, so that's the influence of earthquake in the direction. So in this case, earthquake motion in direction 1 has influence in direction 1. This has the influence in direction 2. This has influence in direction 3. Okay, so that's why this is called influence vector. Okay. So now once we have the equations of motion, we do nodal analysis, set up the eigenvalue problem, find the eigenfrequencies. Okay, so you find the lambda in terms of omega. Okay, and then find the mode shapes, and then form the modal matrix. Okay, now the mode shape frequencies are given by omega in terms of lambda. Okay, so you can solve for omega from this equation. Okay, so omegas are given by this, and then these are the frequencies in hertz. Okay, so this is a quite reasonable structure. The first frequency is 4.2 hertz, and F3 is 12 hertz. Okay, now using the modal matrix, we can diagonalize the mass matrix and stiffness matrix. And these are the modal participation factors. Okay, so we can evaluate this easily. Now here, it's quite tedious to do this by hand. If you can use a MathCAD, Maple, or even MATLAB to do this, it's much easier. It will save you some time. Okay, now because we have the frequencies, we can find the spectral acceleration. Okay, so zeta, all three nodal damping coefficients are 5%. Okay, so we evaluate. This is horizontal 1, horizontal 2, and this is vertical. Okay, so for all three frequencies, we find the value. Now the question tells us we use this response spectrum. It is plotted here in log scale, and sometimes we plot it in log linear scale. Okay, so and here we are given the critical points. Okay, so 0.1, I will mark a few points, 0.1 here, 0.25, 2.5, 2.5, yeah. Yeah, 2.5. This is horizontal. Red is horizontal, so 2.5 is here. Okay, and 9 is this. And 33 and 100. Okay, so we have these critical points. Now between critical points, between any two critical points, it's always linear. Okay, so knowing the values at the two critical points, you can use linear interpolation to find the value at any frequencies you want. Okay, so the vertical is slightly different with this frequency. So instead of 2.5, this corner is 3.5. Okay, that's the only different point in terms of frequency. Okay, so here we want F1 is 4.19. So that's 1, 2, 3, 4, 4 here, 4.19 here. Okay, go up. We use linear interpolation to find these values from the critical points. Okay, so you use a linear interpolation between these two. Okay, so we find the spectral acceleration values at the three frequencies. And for horizontal, 1 and 2, they are the same, and the same. Okay, vertical is different, so you have to use the blue curve to evaluate. Okay, so make sure when you evaluate your PGA is anchored at the right value. PGA horizontal is 0.3G, and the PGA vertical is 0.2G. Okay, so once we have this, we can use our equation for the modal response, 5.4.1. That's quite back. Okay, so you check 5.4.1 and then evaluate the maximum modal response. Okay, so we combine to find the maximum, to find the relative displacement given by this. Okay, so now I is the direction of excitation. This I is node. Okay, so that's node 1. Node 2. And node 3. Okay, so for node 1, we use this term squared and this term squared. Okay, so this is the SRSS dimension. You find the maximum displacement in node 1. Node 2, we only have one term, so that's fine. Okay, so node 2, and we only have one term, so x2 maximum is q2 maximum. And 3, we have this. Okay, so use SRSS, this squared, plus this squared. Okay, so now we can evaluate each one for each direction. Okay, so this one is for the direction and the 3 nodes. Direction 2, direction 3. Okay, now normally when we have inputs or excitations in 3 directions, we combine the contributions from the directions using SRSS. Okay, so that's this term combined with this term with this term. Okay, so now we get the maximum. Combine the directional contributions. Okay, so now do this for each one, you get this. Okay, for node 1, node 2, and node 3. Okay, so this is for the displacement. To find the elastic force, we use this equation. Okay, so now you expand to find the elastic force in terms of the middle response. Okay, so we can come, and then the overturning moment at the base is given by this. You can derive this quite easily. Okay, now we can combine the moment. Okay, so this term is this term because there's only one term. Okay, so maximum M1 is related to maximum Q2 through this. Now M2 has 2 terms. This term and this term. So we have to use SRSS. So this term squared, first term squared, plus second term squared. Okay, so you can plug in and find the value. Now again, we have 3 directions. So you have 1, 2, 3, and you combine these 3 values using SRSS for directional contributions. Okay, so maybe I write here, these are the SRSS for modal contributions. And this is SRSS. For directional contributions. Directional means 3 directions of earthquake excitations. Okay, so that's an example, and make sure that when we derive the SRSS combination, SRSS or CQC is always used for the last step. Okay, so you find the expression of M, use combination. You find the expression for displacement, use SRSS. You cannot find the maximum bending moment from the maximum displacements. Okay, so be very careful about the SRSS or CQC combination. Okay, we will take a break. Now, also for 8 minutes, please come back at 10 o'clock. Okay, now let's continue. We study lumped multiple degrees of freedom structure. Okay, so this is a slightly simpler case, and it's useful for building structures. Okay, so we can model the n-story building by a stick model. With stiffnesses K1, K2, Kn, and lumped masses M1, M2, Mn. And we use n variables U1, U2, Un to describe the motion. Okay, so now you can set up the equation of motion, and in the matrix form it's this. So here we only look at ground motion in one direction, in the horizontal direction, okay? And again, I is the influence matrix of vector, and it's given by this, okay? And all others are very exactly the same as before, okay? But there is only one ground excitation, UG double dot. Okay, so we follow the same procedure. We apply modal transformation, and we can decouple the equations, and then we have our Q equation. Okay, and gamma is the modal participation factor, and L is the earthquake excitation factor. Okay, now we can find the modal response here in terms of this. So we multiply by omega to make this the acceleration response spectrum, okay? And in the last hour, we discussed the relationship between displacement, velocity, and acceleration response spectra. Okay, so here using the acceleration response spectrum. and we find the nodal displacements, nodal displacement vector in this form. Okay, so in terms of the node shape. And the elastic force is Kx, or in terms of M, given by this. Okay, so you can keep these formulas handy when you do your assignments. Okay, now shear force, it's very easy to find. The base shear is the sum of all the elastic forces. And the overturning moment depends on Fe1 times H1, Fe2 times H2, and Fen times Hn. Hn is the height of the story. Okay, so now base shear is sum of all the elastic forces. And the sum of all the elastic forces, or you can write in the vector form, it's a unit is all elements being 1 times the elastic force vector. Okay, so here it's I, the influence vector transpose times Fe. Okay, so now we have this relationship. Okay, so you can rewrite VB, the base shear, in terms of I transpose times Fe. So we substitute what we had before, and this relationship, we end up with this result. So we need the mode mass, nodal participation factor, and spectral acceleration. Okay, the overturning moment is H times F, sum up for all the stories. Okay, so that's easy to obtain. Now we find the maximum value. AK max is the spectral acceleration for damping zeta and omega k or fk. Okay, so S is the maximum value of this AK term. Okay, so the displacement given by this equation, we can find the nodal maximum value. Okay, so be careful, you are clear about node, nodal, node, and the modal. Okay, so X is X1, X2, Xn. Okay, so this N is the node. And X has contributions from the N modes. Okay, so this K is the mode. And when we combine this, the first subscript is the node. Okay, first floor, second floor, and nth floor. And the second subscript is the contribution from the case mode. Okay, so now we can find the maximum modal response for the case mode. Okay, so the maximum modal. And then we evaluate this. Okay, so that's this replace A by the maximum value. We find the maximum. Okay, so you have this. Now we have the contributions from all the modes. We use SRSS to combine modal contributions. Okay, so this is the nth node, and these are the modal values. Okay, so combine the contribution of the n modes to the displacement of node n. Use SRSS combination. Okay, once you understand this, the remaining is quite straightforward. And we can write the elastic force okay, so now E stands for elastic. K is the mode. Okay, so the elastic force for the n stories contributed by the case mode. Okay, so we also combine the contributions for all n modes and for node n. Okay, and then you can do the maximum base shear. It's given by this. So that's this equation. Okay, so that's also the case mode. So we combine each mode for all n modes and for the base shear. There's only one value. Okay, so that's all for this chapter. And then we have a chapter on seismic design. And today I sent an example to Professor Tang, and he will distribute it. We don't have much time to cover this, so I think we will stop here, and you can read about it on the seismic design. This is mainly based on ASCE Code 7 design guidelines. Okay, but the basic idea using structural dynamics is what we covered so far. And chapter 6 introduce code method following ASC 7, and we will skip that. And Professor Tang told me for next week we will not teach new materials. I will answer questions, and if you have any questions regarding the assignments or the final exam, you can give the questions to Professor Tang, and then I will answer next week. Okay, I think I will stop the lectures because we don't have enough time to cover all the materials in chapter 6, so it's hard. Maybe I will stay around for a few minutes and see if you have any questions.张老师，您问问同学有没有问题？
好的，我来问问同学们。So, does anyone have questions?
What you can think about and then ask next week.
.好的，谢教授，我们要不今天就先到这里吧。
好，那就到这里。那你收集一下那个问题，我们下星期再说。
好的，好，谢谢啊。
Okay, so that's all for today. Thank you very much, everybody. Have a good day. Bye bye.
Bye bye.